For some years now, lightweight construction has become more and more important as a result of increasingly difficult economic conditions with regard to raw material and energy costs, legislation, and environmental influences. Lightweight materials, such as long fiber-reinforced thermoplastics, are increasingly being used in automobile production. Applications include, in particular, front-end carriers, spare wheel wells, battery supports, seat structures, and the underbody shields shown here. The financial efficiency of a fully automated production system becomes apparent, especially in the production of underbody shields for the new 5th generation Golf. An underbody shield for the Volkswagen Golf 5 is manufactured by producing two covered segments with individual dimensions of 1430 by 520 millimeters and a part weight of 1,500 grams. The glass fiber rovings are provided either from a suitable bobbin creel or directly from bobbin boxes delivered by the supplier and are guided to suitable sensors for monitoring. From there, the roving pulled out from the inside of the bobbin is fed into the process in a fiber guidance system comprising hoses and tubes. The separate routing of individual rovings prevents any mechanical interaction between the glass fibers. In the direct process, the matrix is inline compounded. This means base polymers and additives such as couplers, processing agents, recycled materials, colorants and fillers, or those referred to as master batch mixtures, are provided to the compounding extruder through high-performance gravimetric metering stations. Vacuum conveyor devices transport the particular components to the corresponding metering stations. The matrix polymer is molten and prepared using a powerful twin-screw extruder. The fibers are spread out using heated rods, and the lined-up filaments are heated to processing temperature. This ensures that the wetting of the fibers is improved. The glass fiber content can be infinitely variably adjusted by changing the number of rovings and the screw speed of the mixing extruder. Following cutting, dispersion, and homogenization of the fibers in the matrix, the plasticized material strand is discharged onto a double conveyor through an appropriate servo die with adjustable thickness. A cutting device is moved along temporarily and cuts the blank to the required length. A heated tunnel serves to prevent heat loss during the continuous feed of LFD material. Following pre-positioning the strand, the heated tunnel swivels to the side and the blank can be picked up. Needle grippers pick up the blank, the robot swivels, and the blank is positioned exactly in the mold. The heated tunnel closes for the subsequent outfeed of LFD material, and the gripper is positioned to enable the material to be picked up within an optimized cycle time. A high-speed press type DYU 3000-2500 AS is used for forming the component. This press features active parallel motion control with a bed size of 3600 x 2400 millimeters and a net press force of 25,000 kilonewtons. The press is suitable for operation with two molds. Thanks to its high closing speeds of up to 800 millimeters per second and high pressing speeds of up to 80 millimeters per second, with a pressure buildup time of less than 0.5 seconds, the press achieves a cycle time of 20 seconds to manufacture underbody shields in double mold operation with fully automatic component removal and loading of the molds. Diefenbacher is the world market leader for plastics processing presses. A gripper removes the component by picking it up using vacuum cups and, after the robot has swiveled, puts it down onto a gauge to enable the component to cool down in a defined way. Following the defined cooling time, the component is picked up again using the vacuum cup gripper and is transferred to the punching press for trimming. This press is a type XY1000 machine with a bed size of 3000 × 2000 millimeters. Its closing speed is 400 millimeters per second, with a punching at 3 to 95 millimeters per second. The punching procedure trims the component and punches the necessary openings. The secondary operation avoids weld lines and thereby produces an even and high level of mechanical properties in the component. The components are removed by another robot equipped with vacuum cup grippers and transferred to the assembly station. The blanking scrap drops onto conveyor belts that automatically return the trimmed edges for reprocessing. The trimmed edges are shredded to create a high-quality recycled material that can be fed back into the process directly. As a result, production waste can be avoided. Clips are attached fully automatically. Handling systems separate the individual metallic inserts, position them, and attach the inserts directly into the component that has been positioned by the robot. The individual plastic nuts are separated in a subsequent step. Pre-positioning units transport them fully automatically to the assembly stations and check that none are missing. On a test station, the component is automatically checked to make sure it is complete in terms of mold filling and clips. Then, the component is released onto a parts output conveyor. The assembly station for attaching plastic nuts checks that the component is complete directly after the inserts have been fixed in place. The nuts are picked up from a supply and separating conveyor located underneath. The pickup arm swivels through 180 degrees to position the nuts ready for assembly. The handling robot positions the component above over the assembly unit and fixes the nuts by relative movement in relation to the assembly station. After the components have been rechecked, they are placed on an output conveyor by the third handling unit and output from the safety area. This completes the manufacture of the underbody for the Golf 5. The components are removed from the output conveyor and stacked. Only a minimum amount of flash formation occurs, and this is removed after the component has been taken out. Following packaging, the underbody shields are ready to be sent to the customer, Volkswagen. Advantages of the Diefenbacher LFT DILC process. Flexible material composition. Customer-specific coloring and additive input. Infinitely variable setting of the glass fiber content. Material is optimized for the component. Cost reduction by avoiding intermediate products. Single thermal stress on the material. Retention of long fibers, therefore a high level of mechanical properties. Homogeneous fiber distribution, even in ribs. High surface quality. Inline recycling. High throughput. Low material quantity in the process, small startup losses. Reduced screw wear. Low energy consumption. Fast mold and material change. Turnkey production cell with master line control for quality assurance. The extrusion process offers the following advantages over injection molding: short cycle times, homogeneous pressure inside the mold, avoidance of weld lines. Mold is filled without damaging the material, low shearing stress, significantly longer fibers, therefore increased level of mechanical properties, low distortion, particularly in wide area components, thinner walls, thanks to tailored blanks. Lower mold costs, no need for multi-cascade technology. More flexible mold adaptation to the production process and future modifications. Double mold operation is possible. High productivity with constant reproducible mechanical properties. Supply of LFT material for 2 presses by 1 processing unit. Direct input of production trimmings. Simple handling during the positioning of local continuous fiber reinforcements. Horizontal parting plane. Bringing together local reinforcement and LFT outside the mold. Reduction in heat losses. Synthetic fibers can be included with less damage to the fibers.